Hi and welcome to my video today, which is going to be on thin airfoil theory and Prandtl's lifting line theory, and it's based upon basically Unit 48, which is on the RQF system of BTEC. Currently has assignment 2 asks you to, or assignment 2 or topic 2 if you want to call that, asks you to look at calculating the theoretical coefficient of lift and the theoretical coefficient of drag. Now there's not really a lot out there unless you go looking for it to find. Bit weird. Not out there unless you go looking for it. There's not an easy accessible way of doing this currently out there, so that's why I'm making this video, because there's some really good books out there, okay, but the books that I'm going to show you some in a minute. So you got Richard von Mises, right? You've got Mises. I apologise for pronunciation, okay. Fairly good book, written a long time ago, okay, so lots of stuff in there. It mentions, like, I think in here, the B17 has been like the cutting edge of technology when this thing was written. So, but there's some really good stuff in there, right? As well as that, slightly better book I've found is the two books, Fundamentals of Aerodynamics and The Introduction to Flight, okay, by Dr. John Anderson Jr. Now, again, these books are full of equations, full of really good stuff. That's what aerodynamics is all about. But if you're a level 3 student straight out of school, haven't done, you know, GCSE, combined science, bit of physics in there, and then throwing into that stuff is going to just kind of, it is a little bit, it's like a step too far. And that's what education's a bit like. If you give someone something that's accessible and then move them up to that, then they will understand it and they will get it into their heads, and they'll develop an interest in that subject and hopefully bring them forward and think, oh, I'd like to know a little bit more. If you throw stuff at them at level 6, level 5 and things like that, straight away a lot of people will go, this is just too hard, I can't take all this in, I can't really get the grips with this subject. Okay, so what I'm going to try and do with this video is I'm going to try and just introduce some of the mathematics behind it. It's not massively hard as long as you understand where the little symbols come from, and that's what some books sometimes don't do. You open a page and you think, well, what does that symbol mean? What does that mean? Where did that come from? Okay, and that's what we're going to try and do now. So, if you're calculating your experimental coefficient of lift and the experimental coefficient of drag, you will have data to go off. You'll have lift data and you'll have drag data. Now, whether you do this in a wind tunnel using transducers or things like that, or whether you do this on the really good thing that I use for my classes is on the NASA website, on the Glenn Research Centre. They have a thing called Foil Sim, which is very accessible and very easy to use, and I use that, and then you can get some experimental data without having to have too much, and it's nice the way it does it. It produces it nice, and you can change the aspect ratio, you can change your span, you can change all kind of things, and you can change different aerofoil shapes. Going back in the midst of time, I think it used to be you could put aerofoil data into that, and I think that Foil Sim 3 now only gives you basic aerofoil shapes to go off. But they're still, it's going to show you a difference in your results, and it's going to display how different aerofoils and shapes can affect your lift and drag profiles. So your equations you're using for that. Remember your 5 factors affecting lift and your 5 factors affecting drag, okay? And there, I'm going to show them in equation format. So you've got your coefficient of lift there, and you've got your lift, and then half rho, which is going to be your density, and then velocity squared, and then a lot of books and websites and things put S in there. You can put S in there, you can put A in there, whichever. It's your work, as long as you know what it means. So S is the area. Okay, so the wing area. In the realms of the coefficient of lift, you're talking wing area here. Okay, which is just the length times the width of your wing. Okay, so your span times your chord, if you want to use the correct terminology. So your span times your chord, you should get wing area in meters squared. So we'll just put the units that you should be using, right? So if we're doing metric units, we'll have meters squared. That'll be in meters per second. Okay, and that one there will be in kilograms per meter cubed, right? That will give you a lift in newtons, and your coefficient is a dimensionless number. Now your 5 factors affecting that, so what you've got here is you've got density, you've got velocity, you've got size of the wing, yeah, and then you've got the lift itself. So you're missing 2 more factors, and that is the angle of attack and the shape of the wing. So the angle of attack and the shape of the wing, they kind of determine the coefficient, right? So it's based on angle of attack and shape. There's lots of other things in there, like Reynolds numbers and things like that, and how slippy the wing is, and how a Reynolds number people ask me all the time about Reynolds numbers, right? The Fisher-Price version of Reynolds number is basically, if there's your wing profile like that, it's how far, so if we're going to say an L, right, how far back does it start to become turbulent, right? And your Reynolds number will govern how far back the wing will start to become turbulent. So that's based on density, that's based on the medium that you're going through. Reynolds numbers in water or thick air, you know, will be a lot different to thin air. It depends on the roughness of the surface that the air is flown over, so that will govern the Reynolds number. Now that will then come into your coefficient of lift, but we're going to leave Reynolds numbers alone for now. Right, so 5 factors affecting lift. Now what we're going to do is we need our drag as well, so all we do for that, yeah, nice easy formula, change it to that. Yeah, so your total coefficient of drag should be your drag. This is if you know your drag, or if you know your lift, you can then work this out and rearrange your formula so that you work out what your coefficient is. Yeah, I'm not going to go through rearranging the formula, because that should be well within your remit at level 3. Okay, but basically, okay, I will, just since you asked, right? Whenever I need to rearrange a formula, I'll stick that up on the board, right? And I never get it wrong. And that other thing, what was that? That was coefficient of lift, wasn't it? And it was lift divided by some stuff, which was half rho v squared times s. So that's something divided by something else gives me something. That's something divided by something else gives me something. So what I do is I put my lift in there, I put my half rho v as that one, right, and then that's my coefficient of lift. So when I rearrange the formula, which one do I want? Find dead Billy basic stuff, okay? I want to actually find my coefficient of lift, yeah? So that's what I'm trying to work out. Now, if I want to find my actual lift from my coefficient, right, my coefficient of lift times that should give me my lift. Okay, so to rearrange my formula there, CL times half rho v squared times s equals lift. Right, so now we come to calculating a theoretical coefficient. Now calculating the theoretical coefficient of lift, if you've got an airfoil like this, and it's got a curve on the bottom, and it's like that sort of shape, or even just a flat bottom airfoil like that with a pronounced curve on it, yeah, you've got airfoils like that, you're not going to find a formula that fits exactly on that airfoil shape. Even if you've got a very thin airfoil, almost like a hairline airfoil like that, and it's got a curve on it, if that's your airfoil there, you know, a sheet of paper, you're not going to find a formula that fits exactly for that airfoil shape. Okay, if you have a very thin symmetrical airfoil, right, so you've got something like that. Okay, now again, some fighter planes, trying to think off the top of my head, the English Electric Lightning, you know, 50s fighter plane, even certain things like, you know, F-16s and stuff like that, you know, they have thin airfoils to make them nice and fast. Certainly in 1950s jet fighters, your MiG-21 and stuff like that, it's going to have like an airfoil that sort of shape. So if you've got an airfoil with a swept-back wing and a thin airfoil like that, your thin airfoil data will actually match as long as you do something to do with aspect ratio correction, which is what we're going to do it's what we're going to look at now. So these sort of airfoils, you're not going to find a theory that fits exactly, but what we're going to do is we're going to show you two theories that will fit roughly, and then how you can adjust them. And remember, for this is aimed at level 3 students. So what we're trying to do is you're not trying to prove anything. You're not trying to kind of reinvent aerodynamics and say, oh, I understand this and I've worked out a computer algorithm to exactly process that based off that data. You're after a rough calculation theoretically that should match as well. You're after some research, if you want, to find out what matches as near to your experiments as you can get away with. Right? So, what we'll do, we'll have a look at that then. So the first thing to use is thin aerofoil data. So what we're going to do is I'm going to draw the graph up to the top corner here. And this graph here, just make sure this is on the screen because I know me. Yeah, okay. So that graph there, we're going to have angle of attack versus the coefficient of lift. And when we plot that off off the wind tunnel experiments that you're going to do, whether you do that virtually or whether you do that using a wind tunnel, right, you should end up with something like this. And then around about, if you plot it all the way up to 15 degrees on the angle of attack, at around about 15 degrees for a standard airfoil, you'll get your coefficient lift will drop off, and that's called your stall point. Okay. Now what's happened there is the airfoil's gone up like that to 15 degrees, and at that point you're starting to get turbulent flow off the back of the airfoil instead of like nice laminar flow. And then that means that your lift's going to drop off. You're going to produce less and less lift because only this part of the aerofoil is now producing lift. So less and less lift, right? And that will tail off towards there until you get no lift whatsoever, until you get the sort of take the mick angle. Yeah, because if you get an aerofoil at that angle there, right, the air is just hitting it and going, what do you want us to do over here? You know, it's ceased to become an aerofoil really. Okay, right. So, without going off too much of a tangent about what's happening, let's stick with the theory and let's stick with the graphs. If you use this theory here, which is thin aerofoil theory, which is a very simple one, it's just 2 pi, this is to work your coefficient, right? So coefficient of lift equals 2 pi times theta. Now this theta is going to be your angle of attack, right, in radians. Okay, now to convert degrees to radians, you multiply by, poor preparation on my point. I'm going to pause the video a little bit while I just revise what I'm supposed to be talking about.